Right, I'll be a radio astronomer. And I went through high school intending to do a physics degree because I thought that's a good preparation for any kind of astronomy, particularly radio astronomy. And if I can't get a job as an astronomer, I'm sure I can get some other good job. So I did physics at school and then went on to university to do physics. Most of my secondary schooling was in a girls' boarding school. Parents were keen to get us out of Northern Ireland for some of our education, and we all got sent away to boarding school in the north of England. Girls' schools had trouble getting good science teachers. I can remember our chemistry teacher. There was a chart of the periodic table up on the wall above his head, you know, listing all the elements in a sort of grid pattern. And we said to him, why is that sort of laid out like that? And he said, God made it so. I don't think he understood the electronic structure of atoms. Girls' schools had difficulty getting good science teachers. Our physics teacher was an excellent teacher. He'd come out of retirement for a second time to teach us. And he was a very, very clear teacher, albeit with a Yorkshire accent. So we learned gems like you slew up on the slope. Do you understand that well enough? He gave me free run of the physics laboratory in the evenings. This is a boarding school, we're living there. Health and safety would not permit it these days. And I decided to make a great big plot of the magnetic field of a bar magnet. So I went to the magnet drawer, chose my magnet, put it on the bench, got this big sheet of paper. Physics teachers probably know what's coming next. I didn't, and started plotting. And of course I didn't get it done in one evening. Next evening, come back, get out my bar magnet, and I can't get it aligned with what I was doing last night. Magnetic field comes through desktops. Don't work on top of the drawer where the magnets are kept. Because if somebody's been into that drawer during the day, all the magnets will have got rearranged, and the magnetic field here is different. Lessons that you learn for yourself are always very powerful lessons. So in spite of some good teaching and quite a bit of rather poor science teaching, I got a place at the University of Glasgow to read physics. I ended up the only female in the honours physics class, 49 men and me. And it was the, quote, tradition that when a woman came into the lecture theatre in Glasgow, it was all woman, all wooden, no carpets or anything, all the guys would go. Can you imagine 49 guys doing that and stamping, whistling, catcalling each time you came in? I learned not to blush. You can control your blushing. And sometimes it's necessary to be able to do so. I duly got my physics degree for astronomers in the audience. My final year tutor was a funny little man called Ron Drever. He was at that stage looking to see if the mass of the electron changed when the galaxy went overhead. He subsequently went on to work in gravitational radiation. And I was so impressed by this man, I made a mental note to keep an eye of any field he worked in. And so I was watching gravitational radiation right from its birth, or I should say the detection of gravitational radiation. I knew we detected someday. I wasn't sure I'd be around to see it, but it's happened, yaha! Whole new spectrum opened up. He wrote me a very good reference. I had intended to go to Jodrell Bank. I'd worked there as a summer student. This is part of the University of Manchester with a great big radio telescope. But I didn't get an answer. And while I had worked there one summer, I had been told that they would never take a woman. There had once been a woman student, and she and one of the young men had put the dormitory accommodation to a use for which it was not intended. He bragged. Sir Bernard Lovell, the head of the laboratory, said, "No more women." Interesting which sex bears the brunt of these mutual encounters. So I wasn't going to get into Jodrell Bank, I reckoned, and I applied to Cambridge, which is a huge step for a kid from the provinces like me. And I must say, when I got to Cambridge, it was really, really daunting. It was full of young men who'd had expensive schooling, who were full of self-confidence, were absolutely sure they were entitled to be in Cambridge. In fact, Cambridge owed them, they were so good. And there were very, very few women, and very, very few people from the north and west of the country, which is where I was coming from. So when I got there, I thought, they've made a mistake admitting me. They're going to discover their mistake, and they'll throw me out. But until they throw me out, I'll do my very best, so that when they throw me out, I know I haven't wasted the opportunity. It was just that I wasn't bright enough. This, they've made a mistake admitting me, is what's called imposter syndrome, and it's now quite well recognised. And if any of the younger people here find themselves in such a position, I'd recommend my strategy. Work your very hardest, so that if they do throw you out, you'll know you've done your best. They probably won't throw you out. But of course, you don't feel confident enough to know that. So I was working very, very hard in Cambridge. Discomfort increased slightly when, within the first week, each of the new grad students was given a set of tools. These are my tools. Still have them. They're the first tools I ever owned. These are not microelectronics tools. These are full-size, full-weight wire-working tools, because I'm going to be doing quite a lot of heavy work. I spent the first 2 years as one of a group of about 6 people building a new radio telescope. I'll show you a picture of it in a minute or two. My particular responsibility was all the cables and connectors and transformers, because when you go from cables of one impedance to cables of another impedance, it's like the signal has to meet a step and you have to help it over the step. It was a huge antenna. It covered an area of 57 tennis courts. So really, really big. Lots and lots of wooden posts. 120 miles of wire and cable, over 1,000 wooden posts. It cost £12,000, which I guess would translate as about $15,000, maybe $20,000. Not millions, thousands. So it was cheap, even by 1960 standards. This particular photograph, this is me, this is my technical assistant Don. We've got some low-loss cable which stretch from here down to another little red and white hut there. I've spent some of the Cambridge winter sitting in this little hut, putting plugs and sockets on the ends of the cable and on the other ends of the cable, and we're now checking the impedance, checking that the contacts are good. So I've got a slotted waveguide here. Working in the field is surprisingly hard work. Even soldering in the field is hard work, because the wind cools the soldering iron. It's not trivial. This is the finished antenna. The most obvious things are the wooden posts. Their job is to keep everything up above wet grass. And most of the action is up here at the top. You can see some copper wire. There was miles of copper wire. Operated as an interferometer. It's really very simple. A bit like a diffraction grating with lots of rows, lots of lines on it. University of Cambridge at that point had one computer. This is about 1967. That one computer was pre-transistors, and it occupied a whole room. And very few people could have time on it. It had memory like your laptop, or maybe like your last laptop. And very few people could use it, and we didn't have time on it. We also were still using vacuum tubes, what we call valves in Britain. Transistors were unreliable, were noisy. We use valves. And they did have one advantage. If your radio receiver is misbehaving a bit, what you go and do is that. And that actually serves to reseat the vacuum tubes, the valves, and quite often makes it work. But we didn't have access to a computer. Just briefly, what's going on here? Way up top in this diagram, way up there, there's a quasi-stellar radio source. My job was to find more of these. They were very, very new, sexy and puzzling. And the signal from this quasar comes down to a radio telescope, and as it comes through the space between the sun and the planets, it's coming through a plasma called the solar wind that's blowing out from the sun. And this plasma is not smooth. It's got clouds with a higher electron density. For the physicists, it actually acts like a diffraction grating, but it's a diffraction grating that's blowing out all the time. And so some of the time a beam comes to your telescope, and some of the time the telescope doesn't pick up a beam, and then the next beam comes and it doesn't. And the intensity you receive jumps up and down like this, quite fast. That's 1 second. It turns out that quasars, which at that point were the very sexy object, are very compact objects, whereas radio galaxies are quite extended. And when you have a pattern like this, an extended object, you see through some of the clouds and some of the gaps. But a compact object, you sometimes see through a cloud, sometimes see through the gaps. So a compact object keeps changing its brightness, scintillating. So this turned out to be a neat way to pick out the compact objects, or the quasars. You look for objects whose signal is fluctuating like this. This is 1 second. Which means you've got to observe with a short time constant, a short integration time, or you smooth out the fluctuation you're looking for. Which means your signal to noise is poor because you can't integrate over a long time, so you need a large area of radio telescope, which is why that radio telescope was the area of 57 telescopes. So I spent 2 years helping build this thing. Most of my work was with the cables and transformers and plugs and sockets, but I did a bit of hammering post into the ground, and I could swing a sledgehammer. I was also playing field hockey at the time, and I could hit the ball from one end of the pitch to the other. And the rest of my team would sort of watch the ball go by and say, "Oh, Jocelyn, never thought to get running." But don't mind, their problem. The university at that time had one computer. University of Cambridge, top university in the country, has got one computer. Computer did not have transistors in it because transistors were too new. It had vacuum tubes, and it occupied a whole room. It had memory comparable to your laptop, and very few people could have time on it, and we didn't. Our data came out on rolls of paper chart, and here we are, rolls of paper chart. There was 30 meters, 100 foot of this stuff every day. I took 4 days to scan the sky, and then I'd start again, another 4 days, and another 4 days. So each sky scan was 400 feet, 120 meters of paper. And by the end of 6 months observing, I had over 5 kilometers of this stuff, which I analysed by hand. And remember, I'm scared they're going to throw me out. I'm being very, very careful. I am checking everything on that chart that looks at all peculiar. Finding lots of the quasars, it was very good for that. I think when we started there were perhaps about 20 quasars known. By the time I'd finished there were about 200. So it was very, very successful from that point of view. So, yeah, we were doing repeated mapping of the sky. Quasars were very compact, they would show this scintillation. And what we do is spend 4 days scanning the sky, or spend 4 days, telescope set on that declination, sky goes past, Jocelyn, change the declination, sky goes past, change the declination. We would spend 4 days with 4 beams, mapping the sky, and then we'd start again, or I'd start again. So we were regularly surveying the sky. And we had a very short integration time because I'm looking for objects whose brightness fluctuates. You don't want to smooth that out. And it was very successful in that before I started we knew about 20 quasars, and by the time I'd finished we knew about 200. So it really delivered that radio telescope. But I was being extremely careful, paranoid, I think. And in amongst the scintillating quasars, and in amongst the inevitable radio interference, there was something else. Radio interference was quite a bad problem then. Cars were very badly suppressed. And every time a car went down the local road, it could on the radio telescope. But you got to recognise it. And pirate radio stations discovered this radio band that had been kept clear, for them, of course. And it was quite hard to get some of them shifted, turned off. But mostly we did pretty well. And because I'm being so very, very cautious, there's a signal that I don't always understand. What have I done? Okay, press the right button. This is low-level interference. And this is a signal I don't understand. And for the physicists in the audience, I'll sort of explain why they look different. Here the spikes go up and down. Here the spikes go mainly upwards. Here, at least people at the front, can see that between the spikes you can see bits of chart. Whereas at least the left-hand end of this, there's no way you can see the chart between the spikes. You're doing Fourier analysis in your head at this point. To say you can see space between the spikes says it's lower frequency than this one where you cannot see space between the spikes. And you're commenting on the amplitudes. Here they're positive and negative, and here they're positive only. That is Fourier analysis. And you've probably done it in your life without realizing, but you have. So these two look different. And I'm a little bit bothered by this one. Interference is forever with us. Nothing much you can do about it, but just discard that little chart. But this doesn't look like interference. And after I've seen it a few times, my brain says, you've seen something like this before, haven't you? You've seen something like this before from this bit of sky, haven't you? And then it's easy. I'm surveying the sky in strips, declination strips. And each chart for that declination, after I've analysed it, is rolled up and put in something like a shoebox, labelled with the declination. So when my brain says, you've seen something like this before, haven't you? I go for that shoebox and get out all the previous times we scanned that bit of sky. The grad students were in an attic, and there was a wonderfully wide sort of corridor down the middle between our desks. So I tell all the guys, all the rest of the occupants were guys, don't move guys for a minute please. And I get out this box for that declination strip and spread them out on the floor. and line them up. So yeah, it was there. I marked it with a question mark. Wasn't there that time, not that time. I think it's there, though I didn't notice it. I've marked that one. And look, they're all at the same right ascension. They're all from the same bit of sky. At this point, I go to my thesis advisor feeling quite proud of myself, and he basically says, "You bloody fool. All this, whatever it is jammed in about a 1/4 inch, 5 millimeters. We can't see what's going on. We need an enlargement." And with chart paper technology, an enlargement is easy. You run the paper faster under the pen, and it all gets spread out. But I can't leave the chart recorder running at that speed forever, or it gets through the whole roll of paper in 20 minutes. And guess who lives at the observatory putting a fresh roll of paper in every 20 minutes? Next best idea, grad student goes out to the observatory at this point, switches to a higher speed recording, lets it run, and then switches off. And I did that for about a month and made high-speed recordings of receiver noise. The thing, whatever it was, it disappeared. And of course my supervisor was cross. If there are grad students or potential grad students in the audience, you need to know everything is always your fault, according to the supervisor. Don't take it personally. Finally, I got it. And this is that first recording, albeit labelled afterwards. The bottom line is 1 second time marks, and the upper trace shows the signal. And you can see along here that it's equally spaced. Indeed, there's probably one missing there, and that's equally spaced. And there's probably several missing there, and those are equally spaced. The label was added afterwards. Indeed, with a little bit of intelligence, you can know the label was added a long time afterwards, because it's got the number 1. You don't label the first one of anything number 1. It's only when you've got a second or more that you go back and label the first one number 1. And LGM was my nickname. It stands for Little Green Men. Wasn't really serious, but you had to call this stuff something. You couldn't talk about that funny signal at 1919 plus 23 all the time. And it's got this period of about 1 1/3 seconds. Pretty accurately 1 1/3 seconds, which was unfortunate because my thesis advisor reckoned it was probably some kind of interference. Somebody in the lab next door has a signal generator set with a period of 1 1/3 seconds, or something like that. But I didn't agree with him because this kept sidereal time. This comes back 23 hours, 56 minutes later each day, or multiples of that if you don't see it for a few days. And most scientists don't work a 23-hour, 56-minute day, only astronomers. But, well, maybe it was some of the other Cambridge astronomers. Our radio telescope site was as quiet as we could possibly make it, radio quiet as we could make it. But it was a bit suspicious. It did look very man-made. So, no, it couldn't be local radio interference. It's not Joe Dokes driving home from work in a badly suppressed car. He's getting off work 4 minutes earlier a day, 28 minutes a week. And by this stage, this has been going on for a month or two. And his boss hasn't noticed. It doesn't work. We asked a colleague and his grad student to see, which they had a radio telescope which worked at the same frequency as ours, to see if they could see it. And under oath of silence, they agreed. And I remember that occasion very well. The other grad student was called Robin Collins, and his supervisor was Paul Scott. And the way the telescopes were aligned, mine would see that bit of sky first, and then Robin's would. And There were four of us out there. I, my supervisor Tony, Robin, and his supervisor Paul Scott. And we stood by my chart recorder, and in came pulse, 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 pulse. It was behaving very nicely. And then we went and stood by Robin's chart recorder for his telescope, and nothing happened. And the two academics, Paul and Tony, started walking down this long laboratory. Robin stayed by his pen recorder, and I was padding along behind the two academics, trying to keep up with them in every sense of the word. So what could it be that shows in your radio telescope but not mine? Could it be that? No, it can't be that, but I wonder if could it be da 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 da. Suddenly there's a shriek from Robin. Here it is! He had miscalculated by 5 minutes when his telescope would see it. And it did see it, and in came pulse, 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 pulse at exactly the same rate, 1 1/3 seconds. If he'd miscalculated by more than about 10, 15 minutes, we'd have all gone home and the story would be very different. In many of these kinds of stories, there's a lot of, what if, could have been very different. So it's seen by a separate radio telescope that has its own radio receiver. Now, it still could be some radio interference in the locality, but at least it's not that Jocelyn has wired up the radio telescope wrong, which is what my supervisor was muttering about. But as we continue to look at it, there is an increasing conundrum. It's got quite short, steep pulses, so it must be small. But it's also keeping the pulse frequency, pulse rate, very, very steady from day to day to day. It's not getting tired. It's got big reserves of energy. So it's big and it's small. Yippee, very clear. And it took us a long time to kind of believe that one, sort that one out. A colleague borrowed my radio telescope, and two of the receivers tuned one up in frequency slightly and one down in frequency slightly, and observed with these two receivers. The argument was, as a radio wave travels through space to the Earth, it passes some free electrons that are not bound in atoms. And those free electrons cause what's called dispersion. The optical version of this is a rainbow, the way light is split into its different colours. The radio version of dispersion is that the higher radio frequencies appear before the lower. And if you can see that at the higher frequency, the pulses arrive earlier than at the lower frequency, then if you've got an estimate of how many free electrons there are around, you can get an estimate of the distance. And we made a very crude estimate and deduced that this thing, whatever it was way beyond the solar system, way beyond the sun and the planets, but it's within our own galaxy. So it could be little green men. However, my supervisor argued, if it is little green men, they probably live on a planet that goes round their sun. Now, for the moment, you're all the earthbound radio astronomers, and I'm a little green man, and I'm going round my sun. And I'm going beep, 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 and as I come towards you, go beep, 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 It's what we call Doppler shift. So, Jocelyn, keep observing. We want to look for a Doppler shift. So I kept observing. No Doppler shift. Very hard to explain. Doesn't seem to be radio interference, because two radio telescopes are seeing it from the same bit of sky. And then I suspect I found a second one, looking at traces on my paper charts, my chart recordings. It's transiting at about 2 o'clock, 3 o'clock in the morning. It's December the 20th, almost Christmas time, And later that morning, I'm due to travel to Ireland, to my parents' house with my boyfriend, to announce my engagement, to be married, our engagement. I've got to be there. But I've also got to observe this thing. So 2 o'clock, 3 o'clock in the morning, I go out to the observatory and set up, and bless it, in comes pulse, 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 pulse. The first one pulsed at 1 1/3 seconds. This one was pulsing at 1 1/4 seconds. Similar, but sufficiently different that you really think you've got a second of whatever these are. My supervisor kindly kept the survey running while I was away over Christmas in my parents' house with my fiancé, and he piled the charts unanalyzed on my desk. I came back after Christmas. He was in the meeting, but it was quite clear. Oh, and I was wearing an engagement ring. Ladies, I don't recommend wearing your engagement ring to work. It sends a signal that you're distracted. You might even be quitting work. But I haven't pulled that one through, and I was very proud of that ring. Tony's in a meeting, but he's kept the survey running while I was away, piled the charts unanalyzed on my desk, and it's quite clear what work I need to get on with. So I sit down and start doing chart analysis. And I'm nearing the end of one chart and sort of, which one's that? It's not either. It's not either. Oh, have I seen this before? Let's get out the charts for this bit of sky. Charts are kept in shoeboxes labelled with the declination strip on the sky. Out come the charts, fling them along on the floor. No, maybe. Oh, I marked that one with a question mark. That was very clever. No. Oh, and there's another question mark. Oh, another question mark. This is another one. Wow. Okay. I'll just finish this particular piece of chart I'm analysing and then try and make sense of all this. So I've got about 1 metre of chart left. Here's this thing that I've just found. What? Is that another one? 1 metre apart? Hecate. Finds the shoebox for this lot, get them out. Yeah. Oh, right. At that point, supervisor appears, stands at the end of the desk. Hello, Tony, look at this, look at this. This one's got 1 1/3 seconds, 1 1/4 second. Look, there's another one. Oh, thank you for keeping the survey running over Christmas. Thank you for piling all the charts unanalyzed on my desk. Oh, how many more have you missed? Go back through all your own records. There's now about 5 miles. Still working miles in this country? 8 kilometres. There's about 8 kilometres in these paper charts. He just blithely told me to go through. And I do ultimately go through them and ultimately go out to the observatory and confirm these other 2. So we now have 4. 3 of them are pulsing around about 1 1/3, 1 1/4 seconds. The 4th one has a period of about 1/4 of a second. So it's clearly quite a bit faster. But it is good to have more than one. This begins to look real. This begins to look like some population that we haven't dreamt of before. We duly wrote up the first one for publication, with the 2nd, 3rd and 4th following in another paper. And such is the clout of Cambridge University that the head professor, Martin Ryle, was able to phone up the editor of Nature, basically say, hold the press, we've got something interesting coming for you. Nature did publish it, and just before that edition appeared on the Friday, about the Wednesday or the Thursday, Tony gave a colloquium in Cambridge, gave it a very titillating title, and every astronomer in Cambridge came. And Tony went through what we found and told him mainly about the first one, which was going to be in the paper in Nature the next day, and alluded to the others that were similar but not identical. There were two possible mechanisms for what this was. The first mechanism involves a rotating thing with some kind of beam, which is the picture we now have. Think of a lighthouse beam sweeping around the sky. Every time the lighthouse shines in your face, you see pulse, pulse, pulse. That's the picture we now have, we believe to be correct. But another possibility is there's something vibrating. And for the astronomers, he was thinking of a star called a white dwarf. A white dwarf vibrating. And each time it vibrates outwards, it launches a shock through its atmosphere. It's a plausible mechanism. The way you tell the difference is watching what happens afterwards. With something rotating, it gradually gets tired and grinds to a halt. With something vibrating, as it gets tired, the amplitude gets smaller, but the frequency gets faster. So the pulses would come faster. But we didn't have enough data to see any change in the period ourselves. Tony favoured this model. He reckoned it probably was a compact type of star called a white dwarf, and it's vibrating and it's launching shocks into its atmosphere, which somehow, mechanism TBD, somehow gives a string of pulses, equally spaced. So just before Nature actually published the paper, Tony gave this colloquium in Cambridge, and I say every astronomer in Cambridge came. And there's one astronomer you may have heard of called Fred Hoyle. He's written some very good science fiction books. Fred Hoyle came and sat in the front row. And at the end of Tony speaking, Fred was the first to speak. Tony put forward this idea about an oscillating white dwarf. And Fred, in his best Yorkshire accent, said, "I don't think it's a white dwarf. I think it's a neutron star." And it turns out that Fred was right. Within 45 minutes, he's heard the evidence and hit the right explanation. As gradually became clear, he was a very, very able scientist. He did not love the radio astronomers because we were showing that the universe was evolving, and he wanted a steady state universe. So any way he could clobber the radio astronomers, boy, he used it. However, press took considerable interest in this discovery, and Tony and I did a lot of press interviews, and they tended to take a very familiar form. The interviewer would ask Tony about the astrophysical significance of this discovery. And then they turned to me for what they called the human interest. What were my bust, waist, and hip measurements? How many boyfriends did I have? Would I describe my hair as brunette or blonde? God. They were not in the least interested in a young woman as a scientist. You were a sex object. And Tony, I'm afraid, did nothing to help. So I just had to kind of bear it. In a sense, the photographers were the worst. You know, please could I undo just some more buttons, please, for the photograph? It was really, really horrible. They just could not accept that a woman was a scientist. Young women, sex objects, period. But one of the interviewers from the Daily Telegraph, a rather conservative newspaper, but otherwise quite respectable, came and said to us, "What are you going to call these things?" And we'd given that some thought. There were two possibilities: pulsating radio stars or pulsed radio stars. And we opted against pulsed, because that might imply an agency making the pulses, little green men. So we said, pulsating radio stars. And the journalist said, no, short name. What about pulsar? A bit like quasar, which we already have. And pulsars they became. and that's due to the science correspondent of the Daily Telegraph. How am I doing for time? Slow, oh dear. Right. Can you take a little bit more? One of the delights of having discovered pulsars is every so often somebody comes up to me and says, you know, I nearly discovered pulsars, and tells me the story. And these stories, I think, are also of value, also of interest, but they show us how science works. So the first story is way back in 1957. We are in McDonald's Observatory, and it's an open night. McDonald specified that the observatory, the telescope, had to be open to the public one night per month, and it's one of those open nights. And the telescope is set on the Crab Nebula, which is the remains of a star that exploded in 1054 AD, observed by the ancient Chinese. And there's a funny little star in the middle of the debris of that explosion. And telescope is set on that funny little star called Minkowski's star. And the public step up to the telescope and say whatever the public said in 1957. And the young woman steps up to the telescope and says, that star's flashing. Well, we now know that that compact star in the Crab Nebula is the remains of the star that exploded in 1054 AD, and it is a pulsar. And it pulses at about 30 times a second, 30 hertz, period of 33 milliseconds. Have we any Canadians in the audience? Do you know that in Canada the power supply, the lights, used to be at 30 hertz? And some people can see 30 hertz. There were some unfortunate Canadians who could see all their lights and everything. And it tends to be young women who can see 30 hertz. This is a young woman who is telling folk that that star in the middle of the Crab Nebula is flashing somewhere around 30 hertz. It is. We now know it is. But nobody believed her. And nobody followed up. Except the summer students who remembered the story and continued to tell it. In 2007, the Australians have an online catalogue of pulsars, as many as were known back then. And they suddenly get a very excited email from a US citizen, Charles Schisler. He said that while he was working for the US military, he was based in Alaska at the early warning system, looking for Russian missiles coming in.